Thank you, Gwana. And thank you for the invitation, and thank you to all the CAMINO members for this kind invitation to this event. So I'm going to give a short talk about our research and development area that we are involved in UPM, in my research group in UPM, about what is called the intrusion response system. So, just up to now, we have IDS in most of the cybersecurity infrastructures. There are a lot of intrusion detection systems deployed in order to detect either known attacks or anomalies with respect to a normal behavior, which is known as signature-based IDS or anomaly-based IDS. And we have also the IPS, Intrusion Prevention System, which is just IDS with some kind of predefined reactions to intrusions. So what we try to address in this research line is it possible to have an automated intrusion response system which is able to automatically react to an event, helping to the human factor? Because up to now, manual intervention is always needed when a security event is detected in a network. So we have tried to design and to develop a system, an automated system, which is going to help to the network security operator in order to apply the most appropriate answer for a given security incident. And this is our research and development proposal. So this is what we are calling the AIRS, Automated Intrusion Response System. It should receive the detection of a security incident, but it's not. It doesn't need to be just raw data, because we need to react. It needs to have some processed event, which is indeed a security event. It's not just an alarm from any IDS. We need to have some pre-processing, and when this pre-processing is done, then we can try to reason and to react, and in order to infer the most appropriate response for this specific event. So after reception, this system is going to apply the predefined security policies that can be defined by the security operator of the enterprise. It's going to get the context and most of the information it can acquire from the context of the security event, and then it's going to react. So, well, this is not new, of course. This is a research and development initiative. So the first thing we made is just to try to identify any other system in the state of the art which is covering this area. And there are a lot of initiatives that you have in this table. But we try to analyze all of these initiatives, and we came to the conclusion that we need some new proposal that can take into account overall the semantic coherence of the inputs, because this is one of the main inputs, main ideas that we have to take into account. What is called semantic harmonization of received events. We want to define a system which can receive inputs from many heterogeneous input sources. For example, IDS, Intrusion Detection System, security information enterprise management systems, or any other system that can feed us with information about security incidents in our infrastructure. So we need to harmonize and to detect that if one IDS is telling us this security event and another system is telling us another thing in another with another syntax, we have to be able to interpret that these two inputs are in fact the same security incident. So we need harmonization, and for that we needed to have some formal representation of the security information. So ontologies. Ontologies and semantic web technologies in order to represent security information. So this was our approach, just to define an intrusion response system based on ontologies, and to define also the policies and the behavior of our system with the help of these formal behavior languages related to the ontologies. Like, for example, ontology is defined with OWL, and policies defined with SWRL, semantic web real language. So these are the features that we need to comply in our design. And this is the architecture proposal for an intrusion response system. So what we have here is, you know, in the left part, we have the inputs, you know, the IDS, or the Security Information Enterprise Management System, which is feeding us with some new security incidents. So we have an alert receiver, which is going to harmonize all the events to a common definition based on ontologies, and then the reasoner is invoked. The reasoner, the first thing which it's going to do is just to get a snapshot of the context of the networks and system at the incident time in order to detect if there are some anomalies that could be taken into account in order to infer the response. Because maybe it can be a false positive, and it can be an incident, but there are any variation in the context. Everything is normal. So this has to be taken into account. And the reasoner is going to infer the most appropriate answer and response for the specific event, taking into account the input, the context, and the policies, and also the feedback from past experiences and fast executions of this response. So let's go with these components. So the first components are the input components. So you know, IDS, Security Information Enterprise Management Systems, which are external components which have been configured to forward all their events to the intrusion response system. Then we will have the alert receiver, which is going to harmonize all the information and try to map this information into a common vocabulary, which is called the ontology. So we will be able to detect that two different events theoretically are indeed the same semantically event. So the context receiver is going to get the snapshot of the system at one time in order to get the anomaly of the system with respect to a normal one. So this is going to be also very important in order to infer the most appropriate answer. This context, so this have to be two phases. One learning phase, which is going to learn which is the normal behavior of our systems, which just learn there is no security incidents. So all of this is normal operational data. So it will learn about traffic, about loads, about occupations of links or CPUs. And then once that we have the context already established, we need to put this context model in operational phase. You know, now just compare the current context with the learned one in order to detect if this context is normal or is abnormal. Does it have any kind of anomalies? So this is one of the main sources for determining which is the most appropriate response, because if there is a big level of anomaly when a security incident is received, you know, it will mean that the security incident is having some kind of success. So we need to apply a strong response in order to mitigate that incident. So this is what we have in the context. So the next module in our architecture proposal is the main module, which is the reasoner. The reasoner, which is going to, is the main component of the architecture, and is going to try to infer the most appropriate response for a given intrusion. So when the incident is received, this module is going to first harmonize the events to a common vocabulary, to a common ontology. It's going to invoke the context models in order to get the snapshot of the context and try to determine if there is some kind of anomaly with respect to the normal context of our networks. And then it's going to invoke the inference engine in order to infer the most appropriate response. And for this inference to take place, we will need to address some information, security information, which is going to be defined with ontologies, with all language, with some security policies, which are going to be defined with the help of the semantic web rule language, and with some inference engine, which is very used in the web semantic area, which is Palette. So it's going to make the inference, and then it's going to apply the response. The response, which we can have a modular set of response executors in order to apply different kinds of responses. Security policies is the most important definition of our system because they have the metrics, the security metrics of our system, and it defines the behavior of our system. So we have defined rules for evaluating the threat related to a context anomaly, rules, for example, for evaluating the trustworthiness of the intrusion source, because not all the sources will be with the same level of trustiness. We will have rules to infer recommend responses, and we will have rules to select the response, the optimal responses. So after this, these are the parameters which can be taken into account into these security metrics in order to infer the response. You know, the source, the IDS and the source reliability, the security event reliability, context anomaly, the affected assets importance, a short set of parameters which need to be defined and which need to be evaluated in order to select the most appropriate response. So we have defined in this project approach different security metrics already established. So for example, we have here a damage reduction matrix in order to apply the response which is reducing at the maximum level the estimated damage of this security event. We can have some also security rule for defining a minimum cost metric, which is going to apply this security event, incident, for example, seems not very important, so we are going to apply a minimum cost metric, response with a minimum cost. Or, for example, a maximum efficiency metric. We are going to apply the most strong response in order to mitigate at most this security incident. So this is the definition of these metrics in these languages. Well, the inference project is very, you have here in this slide, but it's somewhat complex because it tries to apply one or the other metric depending on the asset, and it tries to select some recommended and then determine the optimal one. I'm not going to explain all of this. So the last one, the last module of this project is the responses, the execution of the responses. So we have some module which is called response executor, which tries to invoke specific responses in a modular way. We can plug and play different response models. For example, we have a module in order to cut the communications, in order to apply a countermeasure. We can have a different responses for this system. And we have developed an innovative response. which is the deployment of an ad hoc honeynet for a given security incident. What it's going to do? If we detect, for example, a security event which is trying to affect web servers, and we will see, okay, you like web services, you want to attack web services, so we are going to build a false virtual scenario, plenty of web servers for you to attack. But it's false. It's a honeynet. It's a virtual honeynet. And a virtual honeynet which is built on demand. And on demand and ad hoc, specific for that event. If we detect that the security event tries to attack web servers based on Windows machines, we will develop a honeynet, plenty of Windows machines with a lot of web servers. We will try to build the most appropriate honeynet for that attacker. So this is what we are using. We are using a tool that we use in the university for didactical purposes, for computer network laboratories, that we detect that it could be also applied for this kind of honeynet dynamic generation. And last one is what the last module is the response success evaluation. Once a response is executed, we try to determine if this response was or not successful. So we try to determine again variations of the context. We see the context at the incident time, and we see the context after the response. If they are the same, it should be that the response was not successful. If the context was different, it could be that the response was successful. So we use the theoretical metric, which is called the range cross entropy, in order to determine the variation of the context for this response success evaluation. So this is in the explanation of this approach, this research and development approach that we have implemented and prototyped in 2 different research projects at UPM. Thank you very much.